Consider the example integral of e to the x sine x dx. Now this is a very common type of integration by parts problem, and it might seem a bit confusing in the beginning because if you take u to be e to the x, then du is simply going to be e to the x and it does not really change the integral. Similarly, if you take u to be sine x, then du will be cosine x, and then you're going to reduce the integral to the integral of e to the x cosine x dx. And so it would seem that this integral is never ending. But actually there is a trick. This integral is going to repeat itself. I strongly recommend you pause the video and try to attempt this question on your own before looking at the solution. Ready? Well, now you might have chosen u to be e to the x and dv to be sine x dx. Honestly, it does not matter which one is u, which one is dv. It's all going to work out the same way in the end. So since u is e to the x, we can say that du is e to the x dx. And since dv is sine x dx, integrating both sides, we should get v is negative cosine x. Applying the formula for integration by parts, we get u times v, which is negative e to the x cosine x, minus v times du. So this becomes plus integral of e to the x cosine x dx. Now you may say that, we just converted an integral of e to the x sine x dx to integral of e to the x cosine x dx. How does that help us? Well, once we integrate the second integral by parts one more time, we're going to get integral of e to the x sine x dx. So let's see what happens. Again setting e to the x as u, but this time I'll call it u1 and cosine x dx as dv1. Applying integration by parts to the second integral, we should get u times v, which is e to the x sine x, minus the integral of v times du, which is integral of e to the x sine x dx. And so we have the integral of e to the x sine x dx equals negative e to the x cosine x plus e to the x sine x minus the same integral e to the x sine x dx. We can convert this to an algebraic equation by simply setting integral of e to the x sine x dx as I. And so our equation has I equals negative e to the x cosine x plus e to the x sine x minus I. Adding I to both sides, we should get 2I equals negative e to the x cosine x plus e to the x sine x. And now finally dividing both sides by 2, we get the original integral I equals, and factoring out an e to the x sine x minus cosine x all over 2 plus c. For the next integral, I again recommend you pause the video and try it on your own. This time try to use the integral equals I trick that we used last time, and it might help you to find this integral. Ready? Let's set u to be cosine of ln x and dv as dx. Differentiating u, we get du equals negative sine of ln x all over x dx, and v is simply x. Applying the formula for integration by parts, we get I equals x times cosine of ln x plus the integral sine ln x dx. And now we can apply integration by parts here again one more time and set u1 as sine ln x and dv as dx. Therefore du1 is cosine of ln x over x dx, and v is simply x. This should be dv1, u times v, which is x times sine ln x minus integral of cosine ln x dx. Filling this out, we have I equals x cosine of ln x plus x sine of ln x minus I. Again, adding I to both sides, we should get 2i equals x cosine ln x plus x sine ln x. Factoring and dividing by 2, we should get I equals x over 2 cosine of ln x plus sine of ln x. And let's not forget plus c. For the next example, I suggest you again pause the video and try it out yourself. If you're having trouble, I can give you this hint. Try to multiply top and bottom by square root of a squared minus x squared. Okay, as per the hint, if we multiply the top and bottom by square root of a squared minus x squared, we should get the integral of a squared minus x squared all over square root of a squared minus x squared dx. And now we can split this integral up into two separate integrals. First integral will be a squared dx over square root of a squared minus x squared, and the second integral is minus integral of x squared dx over square root of a squared minus x squared. Let's deal with the first integral first. Now, if you remember from differentiation, the derivative of arc sine x over a is 1 over square root of a squared minus x squared. And so we can say that the integral of a squared dx over square root of a squared minus x squared is simply going to be a squared, this a squared is just a coefficient, times arc sine of x over a. As for the second integral, I'm going to rewrite this as minus integral of x multiplied by x over square root of a squared minus x squared dx. The reason I'm doing this is because I know that I can integrate just this part of it by substitution. Alright, so we can set u as x and dv to be this thing. Since u is x, du should be fairly straightforward dx. And for dv, if we integrate on both sides, we can perform this integral by substitution. Let's say we set t to be a squared minus x squared. We get dt as negative 2x dx. And so our integral of dv simply becomes the integral of negative 1/2 dt over square root of t. But this is simply the integral of negative t to the negative half all over 2 dt, which upon using the power rule becomes negative of t to the half. But remember, t was a squared minus x squared, and so we have the integral of dv, which is v, equals negative t to the half, which is negative square root t, which is negative square root of a squared minus x squared. Take some time to work through this calculation on your own, if this seems a bit tricky. The important thing is that we have obtained a square root of a squared minus x squared, which is the same as the original integral. Let me remind you that what we were doing is integrating the second integral over here by parts. We had set u as x and dv as x dx over root a squared minus x squared. So applying the integration by parts formula, we get negative of u times v, which is x times negative root a squared minus x squared. And if you remember, this was already a negative. And so the second term of the integration by parts formula, v times du, is going to be positive. But we already have a negative sign over here, so we continue to have a negative sign, integral of v, which is... And so we can set this one as I, and therefore we have I equals a squared arc sine x over a plus x square root of a squared minus x squared minus I. Adding I to both sides, you've seen this trick before, we get 2i equals a squared arc sine x over a plus x square root a squared minus x squared, and dividing by 2, we get the desired integral. I equals 1 over 2 a squared arc sine x over a plus x square root of a squared minus x squared. I highly recommend redoing this example before moving on to the practice exercises. Here is some practice for you. Pause the video and try to do these on your own, and I will reveal the answers in a few seconds.